All right, on Friday, Thursday, we talked about wave behavior. What happens to waves at a boundary when they hit a barrier? More dense, less dense, all of that kind of stuff. We're going to spend probably the first half of today's class just doing some questions that are like that, so you see what kind of things I might ask, okay, in terms of wave behavior questions. And then we're going to move on to standing waves, which are probably, the most in-depth thing that we'll talk about in this unit. So, quick review. If a wave travels from a less dense medium to a more dense medium, okay, when it reflects off the more dense medium, will the reflection be upright or inverted? Remember what happened when the waves hit Beckett the other day? He was the more dense medium. They came back inverted. And if I made a crest, it hit him and came back as a pulse. Right? When we go from less dense to more dense, that's fast to slow. You're going to have an inverted reflection. If you're going from slow to fast, you'll get very little reflection and it will be upright. Okay? The other thing to remember is, at a boundary, wavelength and speed change. If the speed goes up, the wavelength gets longer. They have to do the same thing. If one gets bigger, the other gets bigger, okay? And that's because of this. Frequency never changes. Okay? So if frequency can't change, if that changes, that has to change exactly the same way. Okay? By the same amount, same factor. So that frequency always remains the same. Okay? So using your notes from Thursday, okay, I want you working on, if you have the workbook here, okay, it's the waves in one dimension worksheet. Okay, it's got some pictures in there. Okay, I want you working on these questions, and then we're going to go through them together. They shouldn't take very long. There's some interference stuff there. There's some going from one medium to another stuff. Okay, I'm going to work on those, go through them, so you've got some solved examples to study for your test from. Okay, so I'll give you a few minutes to kind of get ahead of me. Okay, and then we'll go through them. Okay, let's look at a few of these here. So for this one here, which medium would be easier for the wave to travel in, the slinky or the string? String, way lighter, way less dense. Okay, so that would definitely be the faster medium. So when the wave gets to A, okay, and reflects back, is it going to be upright or inverted? Right, because there's a boundary between, at point A, that's the boundary between the slinky and the string. Okay, the string is less dense. The wave is going to travel faster there. So will the reflection be upright or inverted? Upright. When it goes into a less dense medium where it will travel faster, there will be very little reflection, and what reflection there is will be upright. Okay, the book I took this out of, they use the term erect. I don't use that because it gets chuckles from immature people like yourselves. Okay, so I always use the word upright, so you might see that if it's not mine. There you go, see. Okay, all right, and then when the pulse, so the pulse goes through A and heads to B. It's tied to the wall. Is that a fixed end? All right, does that represent an infinitely dense medium into which the wave will not travel? Okay, so the reflection off of B will be upright or inverted? That'll be inverted. Anytime it's a fixed end, infinitely dense medium, it's going to reflect back inverted. Okay, so that should answer that question there. Okay, so for A, what happens when the pulse reaches point A? Some will be transmitted, some will be reflected. That's true of any boundary. Okay, long spring runs across the floor of a room and out the door where you cannot see the end of it. A pulse is sent along the spring. After a few seconds, an inverted pulse returns. Is the spring attached to a wall or lying loose on the floor? Attached to a wall. If it was lying loose on the floor, the wave would go from the slinky into the air, which is less dense. and it would be easier for it to travel. If it was lying loose on the floor, you'd get an upright reflection coming back. Because an inverted reflection came back, that meant it was attached to something more dense, like a wall. Okay, if you want to make waves longer on a rope, should you shake the rope faster or slower? Which would make longer waves? Okay, so I'm going up and down really, really quick. Are the waves going to be long or short? They'll be short. So if I want to make waves that are longer, I should have a lower frequency of going up and down. Okay, how many people have done 7? Okay, I'll give you a little bit more time here. If you're done 7, then you can look at these ones here. All right, one property of a wave never changes. That could definitely be a multiple choice kind of question for sure. Okay. All right, now looking at these two waves, is this just like the question on the quiz? It is. All right, so these two waves, are they in phase or out of phase? They are in phase. When one is up, the other is up. They're in phase. All right, now the red line's got an amplitude of +2, the blue line an amplitude of +4, and then obviously minus in the other spots. Okay, so I'm going to use green to draw the resulting wave. It's got to go up to +6, down to -6, up to +6, down to -6. Okay, not the greatest wave, but that's what it should approximately look like. Okay, and my wave needs to go through equilibrium when that wave goes through equilibrium so that they stay in phase. Okay, everybody with me on that one? Okay, now is that question? That's question. Okay, how many people are done 10? All right, I'm going to give you a few minutes to work on 10 and 11, okay, and then we'll go through 10 and 11. So 11 is a 2-speaker question, okay, you can refer back to your quiz as well as your notes, okay, for how to solve those, and we'll go through them together. Guys? All right, so in the diagram at right, what kind of interference is occurring at G, I, K, and O? So all we're looking at are the waves in phase or out of phase at these points. Okay, so at G, this one's up, that one's up. Constructive or destructive? Will the amplitude get bigger or smaller? When I add 1.5 to 4, I get 5.5. So this would be constructive, right? At I, okay, so right here, I've got one that's negative and one that's positive. So is that going to be constructive or destructive? That's going to be destructive. Okay? These waves don't have the same wavelength. They don't have the same frequency. Okay? It's only going to be chance that they'll interfere constructively or destructively at any one point. They're certainly not going to make a pattern of any kind because they don't have anywhere near the same shape. This is just asking, do you recognize when one is up and the other is down that that's destructive? Okay? So at point K, down and up, that would be destructive, and at O, down, up, that would be destructive as well. Right? Okay. Then we got our 2-speaker question here for the last one. So the sound that they're hearing is 400 hertz, so we have F. Okay, the sound is moving at 340 meters per second. All right, and they're standing 6.8 meters directly in front of one speaker. And the speakers are 6.42 meters apart. Oh, that's a big curve in that speaker line, but you get the idea. Okay, so things I've got to know. Wavelength. Okay, so 340 over 400, just V over F. Okay, so 0.85 is our wavelength. Okay, I I need to know how long this side is, so okay, square root of 6.42 squared plus 6.8 squared. Okay, so 9.35 for this side. Okay, so now I need to know how many wavelengths are there from each speaker to the observer, from each source to the observer. So that'll be 6.8 divided by 0.85, okay, the length of one wave. Okay, so that's 8 wavelengths. And then, right, and then we'll take this number here and divide it by 0.85. That's 11. Okay, 11 minus 8 is 3 wavelengths. Whole number, loud or quiet? Loud, yeah. Okay, it's not a 0.5. It's anything other than 0.5, okay, then you're looking at a constructive interference. They're meeting in phase. All right. Okay, questions on any of those? All right. So we are going to talk about standing waves next here. Okay, so if you can find that lesson in the notes. All right. So standing waves are a misnomer. It's a bad name. Standing makes it seem like they're not moving. Waves are always moving. Okay? A standing wave is actually a pattern of interference. You get standing waves if you have a bunch of identical waves traveling in a medium together, reflecting off a fixed end and coming back to the source. Okay? If you get the frequency right, you will get a pattern of interference that looks like it stands still on the medium. These will happen at certain frequencies. Okay? And it is how all musical instruments work, whether it's a string instrument, like a wood instrument, brass instrument, okay? Even drums. Okay, rely on standing waves. All of our musical instruments result from making a standing wave occur in either a string, a column of air, that's almost all of them, okay, or even on like the skin of a drum. Okay, even a banjo is kind of like strings put over a drum. Okay, and so when you pluck the strings, you make the skin of the banjo like vibrate underneath, and you get that standing column of air. Okay? Air columns is what we're going to talk about later on in the week, but it's all standing waves. You get a repeating pattern, interference pattern of waves that just keeps going and going and going and looks like it stands still. So this can be good and it can be very bad. Okay? It depends on what you're trying to do. If we're talking about a musical instrument, we would definitely want a standing wave because it's going to produce a nice loud sound. Because if those waves are occupying the same space at the same time, they all have the same frequency, same wavelength, same speed, then I'm going to get areas where there's a lot of constructive interference. And that is going to increase the amplitude, and then I'm going to hear very loud sounds acoustically amplified. Okay? If I'm talking about a structure, I'd really rather not have standing waves traveling through a structure, and they do. Okay, waves will travel through a structure from things like earthquakes, obviously, but also wind. Buildings have to be designed to withstand wind because wind will produce waves within the building structure. And if those waves are allowed to reflect off the top, which would be like the fixed end, okay, and come back to the bottom, the other fixed end, okay, they'll keep reflecting back and forth. And you generally don't want parts of the building to be experiencing constructive interference. Okay? They're generally made out of more inflexible materials that don't like that very much. Okay? So buildings have to be designed to prevent that. Same with bridges. Okay, especially suspension bridges, because they got big cables, okay, and usually wind can blow across them. Okay? Wind is going to impart energy to the bridge. It's going to push on it. It's going to make it oscillate. Okay? If it starts to get a standing wave, okay, it's going to oscillate a lot. Okay? So I'm going to show you kind of what this looks like. I'm going to get Beckett because he has experience, and experience is really what matters when you're getting a job. So okay, I'm going to get him to act as my fixed end again. All right, this one you're going to want to hold on to tight. Okay. Okay, so if I just start shaking this thing randomly, okay, well, even there I got a standing wave, but if I just like shake it randomly at different, I don't get anything going on. Okay, but a very simple standing wave is just this. Okay, it's always moving a lot in the middle and not at all in front of our hands. Okay, now, how much am I moving my hand? Like maybe 5 centimeters up and down, like on either side of equilibrium. How much is the spring moving? A heck of a lot more than 5 centimeters. Okay? I'm the source of the waves. I'm putting wave energy into this spring, and it's not leaving. Okay? It goes to Beckett, it reflects off of Beckett, it comes back to me, and I keep making more waves with the same frequency and the same wavelength, and because we're not changing the nature of the spring, the same speed as well. Okay? And they just keep amplifying each other. What kind of interference is happening in the middle? Constructive. Okay? Now, if this is, let's say, 1 hertz, let's say I'm shaking it up and down once per second, okay? What will it look like if I shake it at 2 hertz? Okay, shaking it twice as fast. Right? Now I got 2 areas of constructive interference. And once again, how much am I moving my hand? Hardly at all. But that energy stays on the spring. Okay? So it keeps moving, right? And it keeps amplifying. Now what kind of interference is happening right in the middle where that tape is? That's destructive, right? That tape is hardly moving at all. Okay? But there's 2 places where there's constructive interference happening. Okay? Does it seem like the pattern is constant? Right? It's always dead at our hands, dead in the middle, and wildly moving at the other 2 positions. That's a standing wave. The pattern of interference remains the same. You can always see that pattern of interference. But it's the result of waves that are quite small, just going back and forth on the medium and meeting each other in phase or out of phase at the various points. Okay? Now, that was 2 hertz. What if I shake it at 3 hertz? Will we get another pattern? Okay, but I got to get it at the right frequency. If I don't, then I don't get a pattern. Okay, so now I've got 3 places of constructive interference and 5 of destructive, 1 at each hand and 2 in the middle. Okay, what if I shake it at 4? You got to hold on tight because it's going to get crazy now. Hard to maintain them when they get to 4, but there it is. Okay, I don't work up a sweat if I go higher than that. Okay, making sense? Okay, the waves aren't standing still. That's why it's a bad name. It's a standing waves. The waves are going back and forth, back and forth, back and forth. The pattern of interference stands. Okay, there's always constructive interference and destructive interference at the same locations. Okay. Everybody with me there? Okay. So I'm going to show you a quick video here of the Tacoma Narrows Bridge. Okay, so what was the source of energy that got those waves going? Yeah, wind. Okay. Like a lot of people will badmouth the construction of that bridge. Oh, what a terribly built bridge, blah, blah, blah. I would argue the construction of that bridge was incredible. It stood up to those waves for days before it finally collapsed. And we're talking about metal and, and concrete and things like that. And it withstood that kind of abuse for days before it finally collapsed. I would argue it was the engineering of it that was flawed. But it took them almost 50 years to figure out why it collapsed. Okay? They had rebuilt the bridge way before that, but they hadn't figured out why the first one had collapsed. Okay? They knew how to stop it from collapsing again. They knew waves were traveling on it. They just didn't know why the waves got so big. Okay? So the wave energy is blowing across the bridge. Okay? Now, the Tacoma Narrows Bridge is built in a canyon, basically. Okay? And the wind, for whatever reason, for a few days straight, blew straight up the canyon, directly perpendicular to the bridge. So it would push on that side of the bridge, lifting it up, okay? Putting wave energy into the bridge. The bridge was designed to handle that. It was actually designed to oscillate up and down, okay? And take the brunt of that wind. It was never designed to twist, okay? That was the thing they had never anticipated happening. Okay? And the reason that happened was not because wind was coming in and hitting this side, but because of what wind does when you slow it down. So the wind would hit that side and then abruptly push up on it and try and go over the bridge. So you got air coming in on this side being abruptly slowed down and creating a high pressure area on that side of the bridge. But when the wind would go over, it would curl and create a low pressure area on the other side. So one side was being pushed up, the other side was being sucked down by the low pressure area, which was causing the twisting motion they had never anticipated happening. No one had ever seen this happen in a suspension bridge before. Okay, lots of suspension bridges built before that had, oscillated up and down. The Golden Gate Bridge oscillates up and down. It's even designed to handle earthquakes. Okay, but in this particular situation, no one anticipated that much energy being put in for that prolonged a period of time and having that twisting action. Okay? The twisting action is what did it in. Right? But no one had ever thought that that could happen, and it wasn't until they did computer models in the 1990s that they figured out why it had occurred. Okay? Now, how do we stop it from occurring? Obviously, all the waves were identical on both sides of the bridge. The frequency we can't do anything about. The wind was blowing, it was just making waves. But could we change the properties of the bridge and change the wavelength and the speed instead? Okay, so this is how you keep a suspension bridge or a building or anything like that from collapsing. You make it so that the waves that it bears cannot travel at the same speed on both sides, which is super simple on a suspension bridge. You just make the cables tighter on one side. Okay? By making the cables on one side tighter than the other, you make the waves travel faster on that side. Then they can never match up because they'll never have the same wavelength or frequency, because the waves being created they're never going to be identical. Okay, so they're always going to just cancel each other out. They do the same thing in skyscrapers. Okay, they'll build different tensile strengths into the main support beams so that when the building starts to sway in the wind, it can't get standing waves forming in it, because waves on one side of the building will travel faster than the other side, and you'll never get a standing wave of identical means on both sides. That sort of makes sense? Okay, so we're going to talk a bit more about that tomorrow. Okay, I'll show you the design of some of the skyscrapers in New York, okay, where they have to worry about this. Even Calgary, downtown Calgary, I wouldn't call our buildings skyscrapers, but they're still tall and they still face wind. Okay, we'll talk a little bit more about that tomorrow. Okay, reminders. Unit exam is June 12th. Okay, this week we're going to go over standing waves, okay, and air columns. And then Monday, Tuesday, Doppler effects. Okay, Wednesday, unit exam review. Thursday, unit exam. Friday, we'll go over the unit exam. Monday, final exam review. That will be our only day for it, unless we motor through this faster than I anticipate. Which could happen. Okay, but otherwise, it looks like probably just one day for final exam review.